Good morning, dear students. We are continuing with the topic oscillations. And today we are starting that part of our discussion which deals with the different types of oscillations and what happens to the oscillations when there are dissipative forces present, how uh, their amplitude gradually decreases, and how we categorize different types of changes. Sometimes, in order to make up for this decrease in amplitude, in other words, to make up the loss for the energy that is dissipating from these oscillations, sometimes we apply forces, we arrange these systems to oscillate, we create periodic forces, either by using mechanical systems or by pushing with our own hands with a certain frequency. The objects undergo another change, and there may be a dramatic rise in the amplitude. What is that dramatic rise in amplitude known as? What are its disadvantages and advantages? That is the purpose of today's discussion. So let's start with a few definitions, simple ones. And the first one is, what do we mean by free oscillations? By free oscillations, we mean an object is oscillating without any dissipative forces present or without any forces present which is repeatedly pushing that system, repeatedly causing that system to increase its amplitude. Once set into motion, the object is allowed to oscillate on its own, and there are no opposing forces or the forces applied in the direction of increasing amplitude. There are no such forces. So such oscillations which are free without any forces present, they are known as free oscillations. That means a simple pendulum, a spring mass system in which mass is allowed to move in this manner. Once you displace it from the mean position and you allow it to oscillate, there are no forces whatsoever present, and the object and the system oscillates absolutely freely. So that is free oscillations. But in actual practice, there are always some dissipative forces present, some frictional forces are present, some effect of air drag is playing its role. So forces are rarely free. So what is the name of the oscillations which gradually lose their energy, as we observe in the daily life, that any system that is that starts oscillating apparently freely, it comes to rest after a certain time. That is known as damped oscillations. So damped oscillations, this word damped causes another definition. Let's introduce this word first, damping, then I come back to damped oscillations. Damping is the phenomenon in which opposing forces act on an oscillating system to dissipate its energy gradually. So this is the phenomenon in which an oscillating system loses its energy gradually. Loses its energy gradually. So that is known as damping. And we'll discuss later on that damping may be light damping. The system goes on losing its energy gradually, but by very small amounts during each oscillations. It may apparently it may continue oscillating for a very long time, and after only hours of oscillating it comes to rest. In that case the damping is really very light. It may be heavily damped. It takes certain time to come to rest, but it doesn't take long to come to rest. That is of course heavy damping. And then we have another type, critically damped system, in which the even one oscillation is not allowed to complete, and the system quickly is brought to rest. Usually the heavily damped system and critically damped systems are controlled uh, by some mechanical design, and we do not want them to have oscillations in them in the first place. So damping is sometimes introduced intentionally, purposely, because we do not want oscillations to develop in that system. But if we have not introduced any damping and it goes on losing its energy gradually by small amount during each oscillation, then of course it is light damping, and the system is said to have undergone damped oscillations if it goes on oscillating, but during each oscillation it loses some of its energy. So damped oscillations is a fact of life in which some energy is definitely lost during each oscillation. What is the reason of damping? I'm repeating, there are natural reasons. Systems undergoing oscillations do have frictional forces present. For example, a pendulum may have friction at the support where it is tied. It has frictional forces as the air drag causes those frictional losses. So all those systems of this type that undergo some oscillations in air will definitely have some air drag present. So light damping is something that we observe in all oscillations. So dissipative forces cause this energy loss. Let's come to another type of force, another type of oscillations, and that is known as forced oscillations. I add it here. In order to make up for the losses caused by the damped oscillations, we sometimes force an object to continue oscillating. If we observe during the course of oscillations that its amplitude is decreasing and now the object is almost on the verge of losing all its kinetic energy, we apply a push on it, let's say, or we connect it to a system of oscillations, an oscillator, let's say, which causes that oscillations to continue. In that case, the forced oscillations start, and it is no more free oscillations because we have connected that system to a mechanical device, an oscillator for example, which causes these loss of energy, which is caused due to damping. That energy is put in at a certain frequency. It is just like pushing an object, pushing a swing. Every time it comes back to you, you give it a push. So there is a certain frequency of the force that we apply to continue these oscillations, which are gradually losing its energy. So forced oscillations are sometimes required because we want that system to continue. Forced oscillations are applied at a certain frequency. So let me add a little description here. Forced oscillations are the oscillations that are that result from a periodic force applied to an oscillating system. So if a system is already oscillating, but it loses its energy, its oscillations are undergoing some damping, and we want this system to continue oscillations, naturally we need to put in some energy in the form of a periodic force applied to it, and such oscillations that result from this periodic force, which may be in any way we create, that system undergoes forced oscillations. But in this attempt, there is a phenomena that we observe, and that is of interest. And in fact, that is the main topic for today's discussion. That phenomena is known as resonance. When a system is undergoing oscillations and there are no forces present, it is free oscillations. Due to some forces present, they start losing their energy, and ultimately they are almost coming to rest. And in an attempt to make up for that loss, we apply a periodic force. And when we say periodic force, it has a certain frequency of its own. So when we apply a periodic force on the system, it may match with the natural frequency of natural frequency of oscillation of that system. So there are two frequencies present now. One frequency is the natural frequency of the system with which it is already oscillating, and the other frequency is the frequency of that force that we are referring to here, the periodic force. If the frequency of these two things match, it becomes almost equal, then there is a dramatic increase in the amplitude of the system undergoing oscillations, and that is known as resonance. So let me define it first, then we'll explain it with the examples. Resonance is a situation or a phenomenon in which the natural frequency of the oscillating system becomes equal to the frequency of the applied force. The frequency of the applied force. Causing, this is the main thing, causing a dramatic increase in the amplitude of oscillations. of oscillations. So let me describe the main thing. An object is already oscillating with a certain natural frequency, and in the absence of any forces, that is the natural frequency of vibrations. But we have started applying a force to that system, and that is a periodic force with a frequency of its own. If the natural frequency of vibration matches with or becomes equal to the frequency of the periodic force that we are applying, there will be a dramatic increase in the amplitude of oscillation of the system. That means if it was oscillating in this manner, after we apply a periodic force, it will be a very large oscillation with the system will start oscillating, and as a result it may collapse. So there are natural calamities, there are natural phenomena in which uh, objects get damaged due to this effect, resonance. In earthquakes, we have seismic waves that cause the buildings to collapse. We have situations in which bridges collapse, especially the suspension bridges. They start undergoing large oscillations, and as a result, they collapse. And we have instances like that in our recent history. So resonance is to be avoided in many situations, but let's discuss its advantages first, and then I'll come to the situations in which it is to be avoided. But before causing its advantages and disadvantages, let's see how it happens. With the help of a graph, we can show what actually happens and what we are talking about. This is the scale, this is the axis on which we are taking frequencies. And this is the axis where we are taking amplitude. Let's say the system is oscillating already at this frequency. This is the natural frequency of the system, and let's label it as F naught. F naught is the natural frequency of oscillation of the system already oscillating, but it is undergoing some damping, and now we want those oscillations to continue, so we start applying a periodic force to it. If that periodic force has a frequency less than this natural frequency, the amplitude will not rise much, and maybe there is a small increase, and it is an amplitude of this magnitude maybe. So if a natural frequency is different from the applied frequency, the force that we apply, then we have a small increase in amplitude. But as we start increasing the frequency of the applied force, and it goes on becoming comparable to this, we see an increase. And this is where the peak is created. Exactly at the natural frequency, when the two frequencies match, we have a peak, and if we go on increasing the frequency of the applied force, the amplitude decreases again. So this is the kind of curve we observe, and this is how the amplitude of oscillating system changes as we change the frequency of the periodically applied force. With the natural frequency of the oscillating system remains the same. So this is the value where the two frequencies match, and the amplitude is very large. In fact, it could be even larger, and maybe we don't see any peak here. It could be something like this. so large, then the system collapse. But if there is a reasonable increase in it, that means we have introduced some light damping to the system. So system is light damped. System has already some kind of damping in place and we have controlled it. So even if the amplitude has gone dramatically to a large value, the system has not collapsed. And as we go on increasing the frequency of the periodic applied force, the amplitude starts decreasing again because there is a mismatch between the natural frequency of oscillation of the system and the frequency of the object that we are frequency of the applied force that we are applying. So as long as the two frequencies are very different, the amplitude is small. But when these two frequencies match, there is a large increase in the amplitude, and that is what the resonance is about. This is known as, this curve is known as frequency response curve. This is known as frequency response curve. This curve tells us what is, even if they have not given us any information about what is the natural frequency of oscillation of the system, and they have given us this curve with these values given, we can infer from this graph that this must be the natural frequency of the system, because although we can change the frequency of the applied force, we cannot change the natural frequency of the system as long as the system is unchanged. Yes, if we change the nature of that system, we change let's say the mass of the spring itself, then the natural frequency of course changes. But as long as the system is unchanged, its natural frequency is same, and by varying the frequency of the applied force, we can study how its amplitude varies, and this is the manner in which it varies. So frequency response curve gives us always what is the frequency at which this resonance takes place. That frequency is therefore referred to as resonant frequency. Resonant frequency is therefore the natural frequency at which the resonance takes place. So as the name is suggesting, you can understand from this resonant frequency, they often ask, after they give you this figure, they ask us to identify the resonant frequency, and it's easy to read it from this graph because it's a grid given with frequencies on this value on this side and amplitude in centimeters or millimeters given on this side. So it's easy to guess what is the resonant frequency of the system. And if you know the resonant frequency, that means you can make many other calculations. You can calculate its angular frequency, you can calculate its time period, and so on. Now, let's come to the situations in which resonance plays a useful role, and those situations in which it plays a detrimental role. So resonance has some advantages. Let me erase this as well so we can write things clearly. Some advantages of resonance. Advantages of resonance. There are many situations in physics that we study and we apply those situations to practical situations, practical problems to take advantage of this effect. The most common one is the microwave oven. In microwave oven, food particles in the food that we want to heat in the microwave oven, they are already oscillating with natural frequency, and the microwaves that we create inside the chamber, they have a frequency comparable to the frequency of those food particles, the molecules inside the food. So once the frequencies of these two match, the large amplitude of oscillation results, and that means large kinetic energy of the food particles, and therefore the things heat up. So as we all know that higher temperature simply means larger kinetic energy of the particles. So if you are asked to describe why microwave oven is or how microwave oven is making use of resonance, and why it results in heating, a simple description needs to be added here, maybe 2 or 3 lines at the most, not a detailed description required. You just have to know that the frequency of food particles, matches with the microwave ovens, the frequency of microwaves. And this causing increased amplitude of vibrations, which means larger kinetic energy, increased amplitude of vibration. So this increased kinetic energy of the particles means higher temperature. So the object heats up in a minute or two simply because of the resonance effect that we have created inside. Number 2, MRI, magnetic resonance imaging, Resonance imaging, MRI, is another useful phenomena, a technique in which resonance is playing an important role, and this is going on in all hospitals in the world now. MRI is done in routine on daily basis, and this is a highly successful, highly reliable diagnostic technique. You are not required to give any detailed description of it, because this is something related to a topic that we'll cover later on. MRI will be studied as an independent topic, and we'll have a comprehensive discussion there. But it is important to remember that resonance, the name itself is suggesting that there are 2 different frequencies matching there, like one frequency, which is the frequency of microwaves, is matching with the frequency of the particles. Similar phenomenon is observed there. There are frequencies of certain particles inside our body, hydrogen molecules, and the frequency of the radio waves which are radiated on our body. So these 2 frequencies match to give rise to an effect known as resonance, and that helps us in making that image. Number 3, another effect that is the result of resonance is the tuning of circuits, tuning of channels. Let's say you want to tune a certain channel in your TV, and sometimes it's automatic tuning. You allow your TV set or your whatever devices you use. Sometimes it's a radio set is also have its own automatic tuning. What the device does is it has a circuit inside which is known as a tuning circuit. That tuning circuit responds to only a certain frequencies present in the air. Like all kinds of signals are coming, but only one frequency is selected or two frequencies are selected, and that device, your TV, your radio station, they are tuned to those particular frequencies only, and those are labeled as particular channels. So this is known as electrical resonance. This is electrical resonance taking place because this is the resonance resulting from the matching of frequencies between an electric circuit and a frequency which is creating the maximum current in that circuit. So that maximum current means some maximum energy is delivered to that system, and that again is something we call resonance. So if you are asked to give a few examples where resonance play an important role, these could be 3 examples, and if you explore this topic on your own, there is a whole variety of useful phenomena available on the internet. There are books available in which resonance is comprehensively discussed. You might find a few more phenomena in which resonance plays an important role, and of course you should explore those things. I stop here. In the next lecture we'll discuss a few disadvantages, and with that we close this topic, and we'll be ready for the next topic. Thank you.